So previously we talked about three kind of processes. One was isobaric. For isobaric, your volume was constant. And second was isochoric. Sorry, for isobaric, your pressure was constant. For your isochoric, volume was constant. And third one was isothermal. Isothermal process. In the isothermal process, what was constant? Your temperature was constant. Temperature was constant. Now one more process is there, that is called adiabatic. Adiabatic process is when your energy or dq is zero, when your energy is constant, or when your heat over here, when your heat is constant. The heat is given by q, as you all know. For a given system, when there is no input or output of your basically heat, that is a adiabatic process. You can think of this as an isolated system. Clear? Is it clear?
Yes, sir.
Okay. Now from here we will talk about, because from here we will talk about first law of thermodynamics. First law of thermodynamics. Thermodynamics. First law of thermodynamics. This is basically a conservation of energy. Energy. Let's say you have a system. Initially, you have a system whose internal energy is, let's say, U1, and you supply what? Energy, certain amount of energy. Then, on applying that energy, what happened? After applying energy, it went to what? U2. U2. And also, certain amount of work is done. Certain amount of work is also done. Plus, work is done. Then your total energy, this should be sum of change in your internal energy plus your work done. That is basically a conservation of energy. If you have a Q amount of heat is supplied to a system and it went from U2 to U1 to U2. Now this is a change in your internal energy plus whatever the amount of work is done, that is there. Clear? This is basically your first law of thermodynamics. Suppose let's say you give for your, let's say your vehicle, let's say for a car, you have a car. What do you supply? Certain amount of energy by putting what? Fuel. Then what will do? Fuel will start your car to move forward. The fuel will help your car to move forward. Now you can see certain amount of work is done. Work is done. Now the amount of energy which you supply by putting a fuel, it will go under different process like combustion and all. Then the total amount of heat which you have supplied has gone in what? Certain amount of work done plus it has changed your internal energy. So that is basically your what? Your first law of thermodynamics. Clear? Now in your for very small change in state, you can write this in form of a differential form. Basically, delta or change in energy will be equal to du plus change in work done. This is basically your first law of thermodynamics. First law. And what are its limitations? So there are limitations to your first law. Basically, this is a conservation of energy, but it does not tell you how the energy is converted to your work. Limitation is it does not tell you how much energy or how much heat is converted to work. This is this limitation. But what is on the plus side? By using the first law, you can find the internal energy of the system. Because this both of these quantities are what you can measure. This is a measurable quantity. The amount of heat which you supply is measurable. The amount of work done that you can measure. From there, you can find the internal energy of a given system. So this is a application of first law of your thermodynamics. But there is also a downside. There is also a limitation, which is it does not tell you how the heat is converted to your work. Clear? Is it clear?
Yes, sir.
Okay. Now from here, I think we can move to your specific heat. Now we move to your first application of your first law. Application of first law. Now you take a process where your V and T are independent. And before that, actually, what you only depends on your two of your parameter. Because as there are PVT, three parameters, so how many combinations are possible? Now, PV is one. Actually, how many? 3 to the 6, 6 combinations are possible. 6 or 6 to 3. 3 are possible. U as a function of what? Volume and temperature. Or U as a function of pressure and temperature. These are the three quantities where your internal energy depends on. This is why, because this U is basically path independent, so this is just the function of only two variables. So keeping that in mind, U where your V and T is independent. So you have to take as a function of T and V. Clear? U as a function of V and T. Now you take a differentiation. Now you differentiate this. After differentiation, what you'll get? D of U will be what? D of F or D of U is a function of both U and T. So it will be del U by del T times of dt at constant volume. This should be a constant plus del U by del V at constant temperature at that temperature actually, function of dV. So this will be the, after differentiating this is a partial differential with respect to T and with respect to V at constant volume and temperature. And this is basically what here du. If dq amount of heat is supplied to the system, dq is supplied to the system, say to an ideal gas, then what you will get? So basically delta Q, you know, delta Q was what? du plus delta W, change in energy, change in work done, or small work done. Or basically and you know the work done is, or delta W is what? P into dV. So basically delta Q you can write in terms of what? du plus P into dV. Clear? Now you substitute du over here. So delta Q will be what? Du is basically what? From substituting from here you can see is du by dt, constant volume dt, plus du by dV at constant temperature at dV, plus P into dV. Now this is here expression. This is also V, sorry. Now, if you differentiate with respect to temperature, then what you'll get? Delta Q by dt will be what? This T will cancel out, so it will be basically du by dt at constant volume plus du by dv at constant temperature, dv by dt plus p into dv by dt. Clear?
Yes, sir.
Or you can take delta q by dt as what? Del u by del t over v, plus you can take dv by dt common. Can we take out? We can take it always out, dv by dt common. So it will be what? P plus p I'm writing over here. Del u by del v over dv by dt. Basically this much. So now can you see certain expression? Basically this, can we turn this into specific heat? Because we know dq by dt, or for delta we can use d also, at constant volume was what? Yes, cv, specific heat at volume. If you all remember, this was a specific heat. Now if you consider if we heat the system, heat at constant volume. If you heat at a constant volume, what will happen? Heat at constant volume, then this will convert to cv, and dv by dt should vanish. dv by dt should vanish because v is constant, so that's why its derivative will vanish. Is this point clear? I think this is clear. So basically we can write at constant volume, if we heat the system at constant volume, what we have to put dq by dt at constant volume. This is also at a constant volume, and du by dv at this also at constant volume, and this dv by dt as also at constant volume. But you know, if the volume is constant, its derivative will vanish. So that's why this will turn out to be 0. So you are left with, now let's substitute this over here. So you will end up with, this is basically cv equal to del u by del t at constant volume. So this is the expression for cp, or specific heat at constant volume. Now let's consider, this is your one expression. Now let's consider another scenario. So we can move from here. Simultaneously we will do. Now if we heat at constant pressure, heat at constant pressure. If we heat at constant pressure, then can you see what will change? One thing is for sure, delta Q by delta T at constant pressure is basically Cp, that you all know. And if we start substituting this over here, then can you see this basically, if the pressure is constant, then not much of the term will vanish. So basically this has to be substituted by Cp. So this will be Cp will be equal to del U by del T, constant volume, plus this whole thing at constant temperature. So pressure plus del U by del V at constant temperature. At constant. I think this was at constant temperature, sorry. This should be at constant temperature, so this is not needed. This was at constant temperature. Here remaining this dV by dt at constant pressure. Now this is the expression. Now from here, can we substitute equation 1 over here? This, I think we can substitute this over here. After substituting, what you'll get, this is Cp is equals to this, we can substitute with Cv plus, then you are left with P plus del U by del V at constant temperature and del V by del T at constant pressure. So basically, or Cp minus Cv is basically what? P plus del U by del V at constant temperature times del V by del T at constant pressure. Now this is your final expression for your Cp and Cv. This gives you a relation between Cp and Cv. Cp you are able to find by using your first law of thermodynamics. Now in case of an ideal gas, you exactly know and there is one more thing you have to keep in mind. When the temperature is constant, when the actually it was an experimental result, but still when the temperature is constant, okay, when the temperature is constant, then there is no change in internal energy. This is very important. When it was experimentally proven that when there is no change in temperature, there is no change in internal energy. For timing, roughly you can think of this as, because this is an intrinsic property. Now, because internal energy was dependent on what? Basically a kinetic energy. For timing, let's just consider kinetic energy. If you consider kinetic energy, then kinetic energy depends on temperature, because as you keep on increasing the temperature, what? It will start moving faster. Clear? Now, if the temperatures remain constant, so there is no change in your kinetic energy. Clear? So that's why your internal energy is also constant under constant temperature. So basically what? Your del U by del T is, sorry, del U by del V at constant temperature should be what? Should be 0. Because there is no change in internal energy at constant temperature. Clear? Is it clear?
Yes, sir.
Okay. So we can write Cp minus Cv as what? From this expression, we can write Cp minus Cv as P into del V by del T at constant pressure. Clear? And for ideal gas, let's consider for ideal gas, what do we have? PV is equals to PV is equals to RT. So now we need V with respect to T at constant pressure. Now let's take a differentiation of this with respect to at constant temperature with respect to at constant pressure. So pressure is constant, so its constant is getting out. So it will be R differentiation of temperature at this will be what? Basically, this is 1. So P into dV by dt times of P is basically R. So basically, if you substitute this over here, then what we'll get? Cp minus Cv is basically your R. So now this is your very important relationship. Basically, your difference in your specific heats are constant. This is also known as your Mayer's equation, which we have done previously. Now we are proving using your first law of thermodynamics. This is your Mayer's relation. Previously also, I believe we have done this. So finally, we are able to write in constant temperature also one can write but for a time being, I think it's sufficient because we have already found the relation of Cv and also we have found the relation of Cp. Is it clear? Any questions?
Yes, sir.
So by using the first law of thermodynamics, basically a first law of thermodynamics is conservation of energy. By using your first law of thermodynamics, we were able to find a relation between your different specific heat. Now, from the previous equation, we had what delta Q was. Still, for our completion, let's do this also. Du by dt at constant volume. Initially at the starting, we had this equation. We started with dV at constant temperature, dV plus P into dV. Now for a process at constant temperature, okay. Process in constant temperature. For the process in constant temperature, what basically a dt should vanish. Basically, what will happen? dt should vanish because there is no change in temperature. So basically, you'll end up with what? Delta Q at constant temperature will be what? This will vanish. This has to vanish. This is 0. So you're left out with du by dV at constant temperature into dV at constant temperature plus P into dV at constant temperature. Now this is, from here you can see, this is the amount of energy transferred in isothermal process. Is it clear? Or do you have
Yes, sir.
So till now, do you have any doubts? Do you have any doubts? Now from using this thermodynamics, this first law of thermodynamics, we can get a few of the relation. Let's consider the isochoric. For the isochoric process, what was constant? Volume was constant for the isochoric process. So basically what? Your dq will be what? First law of thermodynamics tells you dq should be equal to du plus P into dV. Now for the isochoric process, what? Your volume is constant, which means dV is 0, which means when a system undergoes under isochoric process, all of the heat is converted to what? To your internal energy. Clear? Now, if you, for a certain experiment, if you want to find the internal energy of a system, then what you'll do? You consider a constant volume and you start giving heat, then all of the heat will be converted to your internal energy. So the work done is 0 at your isochoric process. Because it is obvious from this plot of PV also, one can directly see P versus V diagram. When the volume is constant, then it will be a straight line. So there isn't any area under a curve. So that's why your work done is 0. Clear? Is it clear? Is it clear or not? Any doubt? Any doubts? Any doubts still here? And for your isothermal process, one is obvious. A second one is isobaric. For the isobaric process, it will remain as it is. Then the total amount of heat will be what? Del Q will be del U plus P is constant. It will sit over here is same. For isobaric process, nothing changes. So that's why it will give you a maximum amount of work. Because if you go roughly for a given point from here to here, then it will be what? From point here to here, then a lot of area will be covered. Now for the isothermal process, temperature was constant. When temperature is constant, we have seen that your internal energy is T is also, or change in your internal energy vanishes. So basically by using this law, we can get dq is equals to, sorry, this was du is 0 plus dw or delta w for timing. We can just write del q is basically p into dv for the isothermal process. Isobaric is done, isothermal is done, adiabatic is also done. For adiabatic process, all of your work done will be come from what? From your internal energy. Because that is the case, because we are not supplying any energy. All of the work is done by the system. Clear? Because we are not supplying any external energy, so that's why. So tomorrow we are going to do this adiabatic equation of perfect gas. So we are going to stop over here. So are there any problem or are there any doubts? You can ask now. Okay, then fine.